I know we're competing with exoplanets 3 in virtual, no, where is it? Heidelberg, I guess. So I'm glad you made it over to virtual Tucson. I'm pleased to introduce Molly Kosiarek today. She's a 5th year graduate student, NSF graduate fellow at the UCSC, working with Ian Crossfield. But I just found out that she's spending the next year in Tucson, actually, at the U of A. So even though we're not physically in the same building, yeah, welcome to Tucson, I guess. I want to ask everyone to hold on to your questions until the end. There will be a Q&A moderated by me and Serena. But if you have any clarification questions, feel free to type them in the chat. I'll be keeping an eye on the chat window. So with that, Molly, please go ahead.
Thank you, Sebastian. Yes, my name is Molly Kosiarek. I'm a 5th year graduate student working with Professor Ian Crossfield. And I am spending my last year working from Tucson, so I'm really excited about meeting you all once it's safe to be in the office again. My work focuses on understanding stellar activity in order to derive accurate planet masses through the radial velocity method. So today I'm going to be talking about using photometry to understand stellar activity and then using that information to inform our radial velocity fits. Here's the outline for my talk today. I will first introduce my scientific motivation, so really the question of what are planets made of, and describe how stellar activity is impacting our ability to measure planet masses and understand compositions. Then I will introduce Gaussian processes and use the K2291 system as an example application of how one could use Gaussian processes and photometry data to improve radial velocity results. Afterwards, I will describe using solar data to test the effectiveness of this method through investigating the stability of solar photometry and examining the similarities between activity signals in photometry and radial velocity data. And then lastly, we'll end with my current work detailing 2 additional exoplanet examples, one benefiting from a Gaussian process and one that doesn't. So the science driving question for me is, what are planets made of? And this can be broken down into 2 main questions. First, when do planets transition from being rock-dominated like our Earth to volatile-dominated like Neptune? We've discovered a multitude of planets with an intermediate size. A couple of example ARTIS renditions of exoplanets are shown in this figure, and I'm interested in where and why that transition takes place. The distribution of planets between Earth and Neptune has an interesting shape, which may shed light on where that transition occurs. I'm showing here a histogram of the number of planets as a function of radius from Fulton et al. 2018. This bimodal distribution has a gap at around 1.7 Earth radii, which suggests that there may be a compositional change occurring there. So for my thesis, I've been analyzing systems with planets in and around that gap to derive their planet masses and therefore understand their bulk compositions to investigate this transition. The second sort of main question is, what types of atmospheres do small planets have? We have a large diversity of atmospheres in our own solar system, even among planets relatively similar in mass and radius, like Venus, Earth, and Mars. Exoplanets also show signs of a great diversity in atmospheric composition. As a field, we're nearing a large enough sample size of transmission spectra to look for correlations between spectral features and other planet parameters. This plot shows the transmission spectra of 6 sub-Neptune planets, where the amplitude of the features correlates with the planet's equilibrium temperature. A larger sample is needed to understand why this correlation occurs and to look for relations with other planet parameters. So, how can we go about answering these questions? To look at the composition of a planet to first order, one can measure the radius and mass to calculate the bulk density. For further study, we can calculate the surface gravity and combine it with a transmission spectrum to determine the atmospheric composition. And for both of these trees, the mass is essential. In terms of bulk density, mass radius diagrams are used to try to place a planet's bulk density into a context with other planets and in context with compositional models. As shown in this figure, the location of a planet can give a quick view of compositions consistent with the planet's planet parameters of mass, radius, and sometimes flux or temperature. Small uncertainties on the mass and radius are needed for this to provide a useful compositional constraint. On the other side, atmospheric composition can be investigated through transmission spectroscopy. Transmission spectroscopy measures the scale height of the atmosphere as a function of wavelength. And the scale height is dependent on both the mean molecular weight and the surface gravity. Therefore, precise mass is needed in advance to break this degeneracy and to understand the molecular composition of the atmosphere. Since mass measurements have a wide application in understanding planet compositions, my work has really focused on measuring masses with the radial velocity technique. Through instrumentation advances, improvements to the radial velocity method have enabled mass measurements for smaller planets. However, we're hitting like a stellar activity noise floor that we must understand in order to improve mass measurements further. Stars produce intrinsic radial velocity variations due to their internal and surface processes that can be taken as planetary signals. As an example, this image shows our sun through its 11-year magnetic cycle. Additionally, many of the features on the solar surface shown in these images cause radial velocity variations as the sun rotates. Overall, the timescales of these stellar processes range from a few minutes or hours for P modes and granulation to days or years for stellar rotation and large-scale magnetic cycle variations. I will be focusing on stellar rotation during this talk, since this timescale often overlaps with planet orbital periods. The HARPS North team has been studying our sun through their spectrograph over the last couple of years. This is the total radial velocity signal from our sun, and these large-scale variations are caused by planet orbits. So if we subtract out all of the solar system planet signals, these are the residuals, and there's a 5 meter per second residual signal caused by the sun itself. As a comparison, the Earth causes a 10 centimeter per second radial velocity signal, shown as that little purple line. So if we're trying to detect Earths around other solar type stars, we must first characterize to really understand the stellar activity. So now I'm going to transition into discussing how one could characterize the stellar activity signal in radial velocity data using a Gaussian process. To start, what is a Gaussian process? Gaussian processes are a way to model correlated noise and functions that cannot be parameterized directly. They can be fully specified by a mean function and a covariance function. Here on the right shows an example. The small blue crosses are the data. The blue line is the Gaussian process describing the covariance of the data. And the gray shaded area represents the 1 sigma uncertainty space of all of the Gaussian process parameters. So to review, what are we trying to model? Stellar activity occurs in 3 main timescales, and we're focusing on the sort of middle one, the stellar rotation that occurs over a number of days. These signals are stochastic. They often match the timescale of planet orbital periods. They're quasi-periodic due to a combination of periodic stellar rotation and evolving active regions. And they're characterized by some degree of smoothness since the active regions change for a finite amount of time. As an example, this is one way that activity was characterized before Gaussian processes. So this equation is from a 2012 paper on alpha Sun B that fits sine waves at the rotation period of the star and significant harmonics. So this stellar activity analysis added in 23 free parameters for only the star. So really this type of analysis required a large amount of data in order to understand, in order to fit all of these parameters. In comparison, I'm going to be using Radial to fit radial velocity data. So the stellar signal is incorporated through a Gaussian process with the quasi-periodic kernel. There are 4 parameters for this kernel associated with the amplitude, the active region evolution timescale, the recurrence timescale or the stellar rotation period, and the length scale that describes that smoothness factor. So now let's look at an example of this method. We're going to, in practice, using the system K2-291. K2-291 is a solar type star from K2's campaign 13. So we discovered one 1.6 Earth radii planet transiting at 2 days. So the transits are shown here. This star exhibits really lovely periodicity, shown in the top panel. You can clearly see the rotation period basically by eye, and there are signs of surface features evolving from one rotation to the next rotation. The middle panel shows a Lomskargel periodogram of the light curve, peaking at the rotation period around 18 days and a period of 2 alias at around 9 days. And the third panel shows the phase fold of the light curve, which looks really coherent, and that suggests that the active region evolution timescale is rather long compared to the rotation period. So let's compare these periodicities from the photometry with our radial velocity data. Here I'm showing 2 additional periodograms. The top one shows the stellar activity index derived from the calcium 2 H and K lines, which I'm calling SHK. This is sort of an activity indicator of the star in the spectrum. The bottom shows a periodogram of the radial velocity data. The planet period is shown as the dotted line on the left. It's a small transiting planet, so a small signal in the radial velocity periodogram is not unusual. We probably wouldn't have detected this without the transits. There's a strong signal seen near 18 days in both periodograms and with both instruments, both HIRES and HARPS North. This matches the rotation period seen in the light curve. Therefore, this 18-day signal in the radial velocity data is likely caused by the star, and it should be accounted for the radial velocity fit to accurately determine the planet properties, especially since it's a much larger signal than the planet signal seen in this periodogram. So as I mentioned before, I'm using Radial to fit the radial velocity data, including a Gaussian process, to account for the stellar activity. Radial velocity data, however, is often sparsely sampled over a long baseline, which can make it difficult to characterize both planet signals and the activity signal from only this data set. Therefore, I'm informing priors on the Gaussian process parameters from a fit of the K2 data with the transits masked out. The K2 data is sampled every 30 minutes, so it has a really high cadence, and with the transits masked out, it should have only stellar information. So this should produce a really nice prior for all of these Gaussian process parameters. This is a portion of the posterior corner plot from the fit of our K2 photometry. And as you can see here, the K2 photometry does provide quite strong constraints on these 3 Gaussian process parameters. So I'm using these 3 marked posteriors as priors for my radial velocity fit. I'm leaving out eta 1, the signal amplitude, since it's really difficult to translate an amplitude from photometry to radial velocity data, since activity shows up in different ways. Eta 2 is the evolution timescale, and it's constrained to be around 25 days. The eta 3 is the recurrence timescale, so this should be close to the rotation period, and it's at around 19 days, which is really close to the 18-day peaks that we saw. And eta 4 is the length scale, and it's really close to 0.4, which is very close to 0.5, and 0.5 is sort of the expected value from theory, where some authors simulated light curves and looked at sort of how a light curve with spots in multiple places, when looked at only in photometry, can often be derived back to a light curve with only 2 spots. So that produces that 0.5 value. Now let's talk about the radial velocity fit where we're using these values, hence the priors. So we collected 75 radial velocity measurements over 1 season with HIRES and HARPS North. The radial velocity fit is that thin blue line, it's kind of behind the colors. The Gaussian process uncertainty space is shown as that colored overlay. And if we phase fold the data over the planet orbital period, you can see a really strong planet radial velocity signal. For this system, the Gaussian process improved our mass measurement significantly. And to look at a direct comparison, let's add in the fit without a Gaussian process. So from comparing the two, a much higher planet signal is seen in the Gaussian process fit, and the precision of the mass measurement was also improved. I suspect that the difference was this dramatic because the stellar signal for the system, as measured from the Gaussian process, was around 9 meters per second, and that's about 3 times higher than the planet signal. So without really modeling the stellar activity signal separately, it caused a lot of contamination for the planet fit. Now that we have a planet mass of 6.5 Earth masses, what type of planet is this? So from the bulk density, this planet looks like a rocky planet consistent with an Earth-like composition shown on this mass radius diagram. It has a high stellar incident flux since its orbital period is around 2 days, and this is a sun-like star. So that high stellar flux likely photovaporized any substantial atmosphere that might have formed with the planet. To conclude, we saw a common 18-day signal in the photometry, activity indicators, and radial velocity data. Therefore, we used the Gaussian process trained on the K2 light curve in our radial velocity analysis. It improved the accuracy and precision of the mass measurement. And with that, we measured the mass of a small rocky planet to 5 sigma with only 75 data points over 1 season. So this is a relatively small number of points over a really short time for a high precision mass measurement of a small planet. So in this system, the Gaussian process method worked really well. So I'm very curious on how widely can this method be applied. And from this work, I was left with a couple of questions about that intersection of stellar activity and Gaussian processes. So how well are we really modeling all of that stellar activity with this particular kernel? And those questions for me were, for this method, one must assume the photometry accurately represents the stellar variability at the time of the radial velocity data collection. But oftentimes, photometry is taken separately from radial velocity data. So for this example, we have the K2 data, and then after the K2 data is finished, the planet's detected, then we start the radial velocity fit. So maybe the star could have changed its activity cycle in that amount of time. And sometimes radial velocity data is taken years later after photometry, right? We're still collecting data on Kepler planets, and Kepler, it's been quite a number of years since the Kepler mission has been going. So therefore, how do the stellar Gaussian process parameters change over time? And how far apart really can the photometry be from the radial velocity data for this to work? Next, how well did the Gaussian processes describe the physical timescales of a star? Right, I showed the 4 different parameters in the Gaussian process fit and sort of connected the recurrence timescale with the rotation period. So the question for me is, does the recurrence timescale actually measure the rotation period? And what physical process is the active region evolution timescale? How does that compare to the star? Lastly, the reason that I used the photometry to inform the Gaussian process priors was because of the high cadence of the K2 data compared to our radial velocity data. How similar would Gaussian process parameters be between photometry and radial velocity data taken with the same cadence over the same period of time? So we're going to test these questions with the star we know the most about, which already has abundant and detailed data collection, our sun. So I'm going to talk about 2 test cases, one looking at a long time series of solar photometry to look at that time variability, and the second directly comparing simultaneous photometry with radial velocity data. So that first question, how do stellar Gaussian processes parameters change over time? So I looked at the Empire dataset, which is a compilation of multiple solar monitoring programs to produce a 70-year time series of the total solar installation from the sun, which is shown here. The large-scale amplitude changes that you're seeing are the 11-year magnetic cycle, and these smaller variations are caused by solar rotation. So to examine this data set in more detail, I focused on individual years of solar data. So first, we're going to focus on determining that occurrence timescale or rotation period with a couple of different methods to see how they compare. The first one is a periodogram. So this is a periodogram of 1 year of solar data, and really just focus on only the blue line. I haven't described any of the other data sets used for this project yet. The stellar rotation period is shown by that thick gray band. The harmonics are shown as thinner lines going out kind of the 2 times, 3 times, 4 times, and going in, so you can have the period over 2, over 3, over 4. In this particular year, the peak in the photometry data set is offset from that rotation period. It's here, it's closer to around 40 days. This is not that unusual. Star spots and other surface features have an uneven distribution. They evolve over time. And therefore, a periodogram, which is looking for nice coherent sine waves, is not an optimal tool to determine a rotation period. Next, let's look at an autocorrelation plot to see how this compares. So again, we're focusing only on the blue line, and the vertical lines show the stellar rotation period and the harmonics. For this year, the autocorrelation plot determines the solar rotation period quite well. So you can see that the highest peak is at the solar rotation period, and subsequent peaks are at the harmonics. However, these were only with 1 year of data. So how do all 70 years fare with the periodogram and autocorrelation analyses? So I'm plotting a histogram of where that highest peak and highest 3 peaks occur for each year, each of the 70 years, in a periodogram on the top panel and autocorrelation plot on the bottom panel. And we're looking at the highest peak and the highest 3 peaks, since oftentimes the highest peak will be at one of the harmonics, and then like a secondary or a third highest peak will be at the rotation period. So I really wanted to take all of that into account on this plot. For the whole data set, the most common outcome was at the solar rotation period. You can see it's kind of a pretty clear peak there. However, there's a really large spread. So the periodogram highest peak matched the solar rotation period 14% of the time, and the autocorrelation highest peak matched 21% of the time. To give credit, this section of my study was motivated by work done by Chani Nava, exploring the accuracy of periodograms for determining the rotation period of active stars in her 2020 paper. And in summary, the periodogram is not very accurate, and the autocorrelation is only slightly more accurate in determining what the stellar rotation period is. So let's explore how well a Gaussian process performs. Quick aside, I'm using a Lumsgargle periodogram in all of this, and since I did this work, there's a couple new periodograms that might be doing a little bit better. There's a L1 periodogram that I recently read about that seems to find the rotation period slightly more often. So I think exploring different types of periodograms could also be a way to look at this. All right, so let's look at how well a Gaussian process performs. So again, this is the 70-year Empire data set, and I'm separating the data into year-long segments and fitting each with a Gaussian process. I'm using year-long segments for this and the earlier part of the study, since it's often sort of it's the same order for the amount of data we collect on other stars. Getting more than a year is a lot of work, and sometimes it's even much shorter, right? K2 has a 80-day time baseline on stars, and with TESS even has a shorter time scale. They have a 20-something day from the individual sectors. So I think another interesting application would be to take much shorter time scales and fit this, but I haven't done that yet. All right, so to look at an example, this is a 1955 this is what the sun was doing. You can see the blue points are the solar data, and the red line is the Gaussian process fit. So the Gaussian process is able to monitor the solar variability quite well, even though it's going from kind of a lower amplitude to a higher amplitude. It's really quite adaptable to this. So I'm going to walk through the 4 Gaussian process parameter posteriors for each year of the 70 years of data in kind of one large plot. To start, this is the amplitude. So I'm plotting amplitude posterior as a function of year, and I'm showing kind of the entire posterior. So this is like a violin plot. You can see the mean and the width on all of those years. And there's a clear 11-year variation matching the solar cycle in this data set. The next one, the evolution timescale. For the sun, the star spot decay time is kind of from a few days to tens of days, depending on the size of the sunspot and where it is in latitude. The active region evolution really should be describing kind of how long it takes whole groups of spots to evolve. And that should be longer than how long it takes single spots to evolve. So I would expect this timescale to be longer than what we're currently seeing here. This third one is the recurrence timescale, which really should match the rotation period of the sun. I've plotted the solar rotation period as that gray horizontal band, as the rotation periods changes slightly as you move in latitude. The Gaussian process matches the rotation period for only a few years. Oftentimes, this parameter is instead constrained at about half the rotation period. You can see, especially towards the beginning of the data set, there's a whole bunch at around 13 days, about half. So we're going to come back to this discrepancy in just 1 minute. But first, the last one is the structure parameter. I'm using a prior of 0.5 plus or minus 0.05. So this posterior is primarily reflecting this prior, so we're not going to discuss it further. To go back to this problem at hand, there were only 7 years that have the recurrence timescale well constrained on the solar rotation period. So I've put little red boxes around those. And you can see that these 7 years have something in common. For all of these, the evolution timescale is longer than the recurrence timescale. But for many of the other years, the evolution timescale is kind of really low. It's sitting at only a few days to like 10 days. And so this might be causing the problem. If the evolution timescale is really, really small, it's a exponential decay term. So it's allowing the model to change really rapidly. And if the model is able to change really rapidly, it's going to have a much harder time sort of modeling the variations at longer timescales and modeling that, seeing the like 20-something day solar rotation period. So to test that hypothesis, I ran a case where the evolution timescale had a prior that it has to stay longer than the recurrence timescale. I'm not putting a prior on where either of those are, only the relative difference between them, that the evolution timescale has to be longer than the recurrence timescale. So that's shown here as the dark blue data. The amplitudes remained relatively unchanged. The evolution timescale increased substantially, and the recurrence timescale matched the solar rotation period for more than half of the years. So from this part of my solar work, it kind of brought me to a tentative conclusion that I would recommend including this prior, restricting the evolution timescale to be greater than recurrence timescale in order for accurate characterization with the Gaussian process if one is using sort of photometry to characterize stellar activity. And if we think back to the K2-291 case, the K2 data fit also had a longer evolution timescale compared to the stellar rotation period just all by itself. It was 25 days compared to the 19 days rotation period. And perhaps that's necessary for this method to work. So the reason that we're characterizing stellar activity in photometry really is to inform radial velocity fits. And so that's only useful if they both describe stellar activity in the same way. So the next step is to directly compare the outputs of Gaussian processing fits of photometry and radial velocity data together. So the HARPS North team has been collecting radial velocity of the sun, measurements of the sun for the last few years. The top panel here is the data, same data that I showed at the very beginning of the talk, motivating, characterizing stellar activity in order to detect Earth-sized signals. The middle and bottom panels show two measurements that can be used as activity indicators. The middle one is the cross-correlation function, flow width half maximum in pink, and the bottom is the bisector inverse slope in orange. So these are two indicators that can be used with sort of a stabilized spectrograph like HARPS North is, whereas with the data set I talked about earlier and the data sets I'm going to talk about later, using high-res, we're using the Gaussian H and K lines, since for high-res we have an iodine spectrum that is also imprinted in the spectrum, and you can't measure these types of indicators. You can only measure like lines. So that's why we're using kind of a different selectivity indicator for the two instruments. Just like we talked about before, I'm splitting this data into year-long segments and then fitting each of the Gaussian process. So I've labeled the 4 years at the very top. Those are the kind of the 4 segments that I'm splitting the data into. Source is the solar mission that I'm going to be talking about for photometry here. It's been collecting data since 2004, and 4 of the years overlap exactly with the HARPS North data. So these 4 years are shown at the bottom here. And this allows us to directly compare the outputs of photometry and radial velocity data taken completely simultaneously to see how stellar activity is measured in both of these data sets. So I'm splitting the photometry, radial velocity, and 2 activity indicator data sets into the same 4 year-long segments, and binning each data set to the same cadence and fitting each with a Gaussian process. And we're going to next walk through the 4 Gaussian process parameters for the 4 data types over the 4 years in a very similar plot structure to the Empire data. So this is the output of the 4 parameters. It's kind of a lot all at once. I'll walk through it though. So each parameter is that different horizontal panel, and the years go from left to right, 1 to 4. The shaded points, sort of shaded sections, have the additional prior constraining the evolution timescale to be longer than the recurrence timescale, and the outline is without this prior. So we're going to spend a little while on this plot, but there are 2 interesting comparisons from the initial fit without the additional prior. So just only look at the outlines for now. First, the source photometry and the HARPS North RVs have consistent posteriors that match the solar rotation period, that gray band, only in year 4, so only in that year. And that's also the only year where the source evolution timescale is longer than the recurrence timescale. Second, the full width half maximum and BIS show opposite results of photometry. So the full width half max data well matches the RVs for years 1 through 3. They kind of, the RVs and the full width half maximum often sort of both have an odd bimodal posteriors, or they're both matching very well. And the BIS posteriors for year 1 through 3 are consistent with the solar rotation period and has a longer evolutionary timescale than the recurrence timescale. Okay, so now let's look at the posteriors of the second analysis. So this is, we're looking at only the shaded points, and this one has the additional prior. The source photometry and the HARPS North RVs are consistent for 3 of the 4 years. So this really helped the 2 data sets become more consistent. And the inconsistent year, source instead has a recurrence timescale at half the solar rotation period. Okay. The additional prior also helps to constrain the RVs and full width half max posteriors for years 1 through 3. They're both better constrained to match the solar rotation period. Year 4 is distinct though, as the full width half max and BIS do not have well constrained posteriors, and do not match the photometry or RVs at all. So additionally, year 4 is the year that's at the solar minimum compared to the rest of them. So it's kind of, these are declining into the solar minimum. And so perhaps solar activity displays different characteristics in line measurements compared to the photometry throughout the solar cycle. Remember, because year 4 was the one that the solar data matched right away, no problem. Whereas the line indicators don't at all. So further cadence radial velocity monitoring of the sun will be important to characterize, sort of confirm many of these observations, and I think potentially detect changes as a function of the solar cycle. So some radial velocity papers have been using photometry to characterize the solar activity, and some are using activity indicators to characterize the solar photometry. So from this, it looks like they both can work, but for some of the years, for the sun, it doesn't work. So we really need to understand why we're using which one, when, and really try to make sure that what you're using makes sense. There we go. Okay, so let's conclude this section and fill in what we now know about the 3 questions that I had about Gaussian processes. How the parameters change over time, how they match the physical characteristics of the star, and how connected they are between the photometry and radial velocity data. So first, we found that the amplitude varies with the solar cycle, and that the recurrence timescale and evolution timescale were relatively consistent over the 70 years of data. Next, the Gaussian process outperformed both periodogram and autocorrelation analysis in determining the solar rotation period. And the Gaussian process was able to determine the solar rotation period for the majority of years. And finally, with an additional prior constraining the evolution timescale to be longer than the recurrence timescale, the 2 parameters were consistent for most of the years between the photometry, radial velocity, and activity indicators. Again, we're kind of looking at 4 years. So I would love to expand this, 7 years from now to a full solar cycle and see how this varies across the solar cycle. All right. So finally, I'm going to walk through 2 more systems fairly quickly, one using a Gaussian process and one without. And this is the work that I'm currently doing. So the first, GJ9827, has 3 small transiting planets in short period orbits, where I'm showing the 3 transits here. Planet B and planet D are both being observed by HST transmission spectroscopy. So it's particularly important for these planets to have really precise masses to help understand the atmospheric composition. And the second system, HG106315, has 2 transiting planets. One's Neptune-sized and one's about half. Planet C has been observed by HST, and signs of water were found, as described by Kreidberg et al. The paper was submitted and it's on arXiv right now, if you're interested. As I mentioned before, precise masses are key to inferring atmospheric compositions from transmission spectroscopy. Therefore, we collected a lot of points on these 2 systems to really update their mass measurements. And I examined the stellar photometry and activity indicators to look for stellar activity to see if we should use a GP analysis for these systems. First, this is the photometry for GJ9827. The stellar rotation is really clearly seen in the time series at the top, and a periodogram analysis produces 2 significant peaks. The longer of the 2 is more likely to be the rotation period. According to Rice et al. 2019, it's more consistent with the inferred age of the star. So let's compare this with periodograms of 2 activity indicators. We're now using SHK and H alpha, along with the radial velocity data. So here I've marked the 3 planet periods, and there's also a peak at the in the SHK data and radial velocity data matching the rotation period of the star. Just right there. So I decided to use a Gaussian process for this analysis, and I'm using the SHK data to inform that fit instead of the photometry, since a Gaussian process fit of the SHK data produced very similar results to the photometry. but the SHK data is taken simultaneously with the RVs, right? It's one stellar line in the spectrum. And so that means that they're completely simultaneous, and whatever activity is happening in the SHK is going to be happening in the RVs, compared to the photometry, which was taken a couple years apart from the data set. So let's look at that fit. We collected 92 observations with high-res, and I'm including 142 previously published measurements from FEES, HARPS, HARPS North, and PFS. The radial velocity fit is shown on the left, and the fit phase to each planet orbit is shown on the right. So from this analysis, we were able to determine the mass of planet B and D to more than 5 sigma, which will really enable the HST atmospheric characterization. So I'm now going to talk about the data analysis of HD 106 through and 5 before describing all of the planet's bulk compositions. So here's the photometry for HD 106 through and 5. There are no clear rotation signals in the time series by either eye, and the sort of periodogram analysis. The star has a moderate V sin I that constrains the stellar rotation period to be less than 5 days. So that's over here. And there are really no clear peaks on that side of the periodogram. So let's compare this with the periodograms of the 2 activity indicators. Again, we're using SHK and H alpha along with radial velocity data. So here I've marked the 2 planet periods, the dashed lines, and the V sin I constraint. So there are no clear peaks in the periodograms of any of these 3. I additionally tried fitting each of these data series with a Gaussian process to look for the rotation period that way, since the solar data project showed that the Gaussian process was slightly better at picking out a solar rotation period compared to the periodogram analyses, but I didn't find any conclusive results in that either. Therefore, for this system, we're not using a Gaussian process in our radial velocity analysis. So we're doing just a circular 2-planet RV fit. We collected 126 binned observations with high-res and include 155 measurements from HARPS and PFS. The radial velocity fit is shown on the left, and the fit phase to each planet in orbit is shown on the right. And from this analysis, we were able to determine the mass of planet C to nearly 5 sigma. So this also helped with the HST atmospheric characterization. So now let's talk about planet compositions. Here are these 5 planets plotted on a mass radius diagram. So GJ9827b and C, these 2, both are consistent with an Earth-like composition of rock and iron. GJ9827d and HD 106-5b are both just below that 50-50 water rock line and the 1% hydrogen helium line. So they're consistent with a substantial water fraction or a small hydrogen helium envelope. And they're a good bit above the Earth-like line, so they do require some amount of volatiles. Then lastly, HD 106-5c is located near our own ice giant planets. It has a much lower density. It's too low to be explained by water alone, and it's consistent with having a 10% hydrogen helium envelope. So we then wanted to explore the compositions of these planets a little bit further by comparing them to model grids. So we compared the mass and radius of each planet with model grids from Valencia 2011 and Lopez and Fortney 2014. The code to do so is available on GitHub at the link at the bottom. We're focusing on 2 models. One assumes an Earth-like rocky interior with a fraction of water, and the second assumes an Earth-like rocky interior with an envelope of hydrogen and helium. And we're sampling the mass and radius space of each planet with 100,000 Monte Carlo trials to assess the uncertainty of both of those parameters, and comparing each of those individual trials with both of the models to calculate the mass fraction of water or hydrogen and helium needed to produce the sample mass and radius. Some of the trials have a mass and radius outside of the parameter space for one or both of the models, And so I'm listing the percentage of trials consistent with the models in that table on the top right, along with the average water and hydrogen helium mass fraction needed for the trials that did require some, that were consistent. To start, GJ9827B and C are both largely consistent with a rock-only composition. The water models have less than 2% water mass fraction, and the hydrogen helium models all report really the lower limit of our model grid. Conversely, HD10635C has a substantial volatile fraction. Only 3% of the trials were consistent with a water rock planet, and the rest were less dense than a water-only planet. All of the models were consistent with a rocky core with a hydrogen helium envelope, and on average, it had a mass fraction of 10% hydrogen helium. So that one's really consistent with what we saw in the mass radius diagram. And now let's view the compositions of GJ9827D and HD106215B in a little bit more detail, as their intermediate densities allow a lot of possibilities. So I'm showing here just a histogram of all of those trials for both planets. And these two are both consistent with either a rock and water composition or a rocky core with a hydrogen helium envelope. The mass fractions of each are shown in histograms on that bottom right. GJ9827D has an average of 31% water, or negative 3.5 dex hydrogen helium, and HD10615B has an average of 35% water, or negative 2.5 dex hydrogen helium. Just to sort of reiterate, these models are really simple two-composition models, so it doesn't allow for water, rock, and hydrogen and helium, or any other like molecule, any other types of compositions. And the compositions will be further explored with the HST transmission spectra data. All right, so lastly, I'm gonna have one more slide about Gaussian processes and then wrap up the talk. So the Gaussian process analysis I described today assume that the stellar activity present in the radial velocity data is related to stellar rotation. It really doesn't, the quasi-periodic kernel is really it is really chosen to match the properties of stellar rotation. So in most cases, this relies on the prevalence of star spots. Hotter stars have fewer spots on their surfaces. Therefore, this method might be less effective for hotter stars in general. HD10635 is an F-type star, so it's perhaps too hot for this method, which might have been why we didn't see the rotation signals in either data sets, and we didn't use a Gaussian process. To investigate this hypothesis, I performed an extensive literature search on the use of Gaussian processes in radial velocity analyses to look at what stellar types have been used for this method so far. So 36 systems have used Gaussian processes so far. So this is a full list of systems and the stellar temperatures. The main sort of what I found here is that all of the stars are cooler than the Kraft break at 6,200 Kelvin. There's only one star hotter than the sun, K2100, which is a G0 star. So all of these systems so far have been MK and G dwarf stars. This is sort of a biased sample because I'm only looking at what systems had a Gaussian process that worked. It's a lot harder to search for systems that someone tried a Gaussian process with, but that didn't work, because oftentimes that sort of wouldn't be published. So sort of initial takeaways is perhaps this method only works on MKG dwarf stars, but further work is needed on this topic before I'd want to say anything definite about it. So let's conclude. First, Gaussian processes can be efficient ways to include stellar activity in radial velocity fits. Our fit to the K2-291 work, our K2-291 work showed that in optimal scenarios, they can improve the accuracy and precision of derived planet masses. Our work with the solar datasets showed that photometry can be a valuable tool for understanding stellar activity in radial velocity fits, especially when photometry is taken at high cadence. In our direct comparison, the Gaussian process parameters were consistent fits the photometry, radial velocity, and activity indicator datasets for most of the years. Additionally, a prior constraining the evolution timescale to be greater than the recurrence timescale helped with the solar data and may help with other stars. Lastly, Gaussian processes seem to work best for cool stars. So I recommend going about Gaussian process fits carefully, as stellar activity can be exhibited differently in stars of different temperature, ages, activity levels, and other parameters. Thank you.